I guess let's get started. Hello, everyone. Thanks for coming. Very happy to introduce Yiping Ma. She's a final year PhD student at University of Pennsylvania, working with Sebastian Angel and Tal Rabin. She has done a lot of work in cryptography, security, and systems, especially private information retrieval, secure aggregation, and federated learning. She was a recipient of the Microsoft Research PhD Fellowship and Morris and Dorothy Robinoff Award for Best Dissertation Research at Penn. And today she's going to tell us about private information retrieval.
Yeah. Okay. Thanks for the introduction. So I'm happy to share today a few of my recent work on private information retrieval. And this talk is based on joint work with Adria, Yuval, Mahimna, Daniel, Bayu, and Mariana. So I want to start this talk with an interesting observation that how your daily interaction with today's online platforms leaks much more sensitive information than we could have thought. So let's try to guess the top 10 search queries, starting with how do you get? I played this game with some of friends before because once I talk to them about how private these information are, they're not always convinced because they think their search queries just leak information that they do not care much, like where they live, where they are working, etc. Okay, so maybe you have an answer in your mind now. And when I showed these actual search queries people make on Google, they're very surprised by how personal and sensitive these information are. And in many times, this is not only your health condition, it's maybe your financial status, your relationship status, and so on. So this query and answer pattern exists in many of today's applications, like not only in search engine, but also in messaging apps, etc. So here we can abstract this as like there's a client, and then there's a database server storing web pages or like messages in user apps. And then the client sends a query to the database server, and server answers back. And in the same way as before, our queries are pretty revealing in all these applications. So what do we do? So not using these services is definitely not a solution. But what if we can magically have some way to obfuscate the query, and the server can still process our query and give us an answer? So in fact, 30 years ago, cryptographers already proposed a primitive called private information retrieval. So this is a simple abstraction like this. So let's say we have a database server that holds the database we abstracted as a bit string of length n. And then we as a client wants to get an entry from the database without revealing which entry we want to get. So basically, let's say I want to get x2, the second bit in the string, but I don't want to reveal the index 2 to the server. And it turns out that this primitive is very powerful in the sense that we can build many interesting applications in a black box we're using here. So for example, very recently, some people built private search engine out of this simple primitive, and some people build metadata private messaging using this primitive. And the efficiency of these applications really rely on the efficiency of the underlying PR protocols because they just use the simple primitive as black box. So the rest of this talk will discuss how we can build a good peer protocol. Okay, so maybe you think peer is magical, but actually there's a trivial solution for peer. So no matter which index the client wants to retrieve, it just downloads the entire database, right? So like, let's say I want to retrieve the third item, I just download n bits. So the server in this case learns absolutely nothing which index the client wants to query. So we have perfect security against the server. But of course, the downside is that the communication is n bits, linear in database size, and the computation at the server is also n bits. You need to basically touch every bit of the database in order to answer that. What is the ideal world we want for peer? So ideal solution is that we can have small communication, small computation at the server, and we can preserve the perfect security that we have before. Okay, but we cannot actually get all we want as theoretical impossibility results suggested. So like over the past 20 years, the peer basically split into like two directions. So if we want to get perfect security with a single database server, then we have to pay n bits of communication cost. This is like theoretically proven. And consequently, we need to relax our ideal picture a little bit. And from here, prior works diverge into two settings. So one direction sticks with the information theoretic notion, and their construction replicate the database across multiple servers. And to get privacy, they need these servers holding the database are non-cloning. The other direction considers a weaker security notion where the adversarial server is computationally bounded. And in such a setting, Kushilevich and Ostrovsky show that there's no need to replicate the database. And as a result, we only have a single server and there's no non-collusion enforcement. Okay, so the green part marks like the benefits of it over the other direction. However, the computational direction comes as a price for performance because most of them relies on hardness assumptions that have complicated cryptographic operations. The computational peer are usually significantly slower than the information theoretic components. So each direction has their own advantage, but in either case, we cannot get best of both worlds because the impossibility result that we saw in the beginning. Okay, so the question asked in this talk is that, what if we relax the peer primitive a little bit? So note that in the classic peer, so I call like whatever I talked before as classical peer. So security should hold even with single client queries database, right? And now we will consider something like more relaxed. Let's say we have many clients accessing the database at the same time. And in that case, we can get security in a fundamentally different way from the PIR in the standard. And what is this model? I'll call this shuffle. So it has two components. As I just said, we assume many clients querying database at the same time. And we also assume those queries are shuffled before reaching the server. So by shuffle, I mean, it's just a permutation. So let's say I collect all of your messages and then like I just permute them and then send to the server. Okay, yeah.
We need those permutation to be some sense perfect?
Okay, great question. So in this talk, let's consider perfect permutation. But in the paper, we do have like result that is with regard to imperfect shuffle. So in that case, you can get some partial security with regard to some like definition. Yeah. Okay, so basically the picture works like this. Instead of we have a single server, single client, now we have a single database server and many clients. And we additionally has a shuffler, which I call this a shuffle server. So all the clients send their queries to the shuffler. The shuffle server sends, like shuffle them, forwards them to the database server. The server can answer to each of these queries, and the shuffler can permute them back and send to the client. Okay, so I want to first say that this model actually doesn't trivialize the peer problem. So why is that? Let's consider all the clients just want to query the first item in the database. All of them sends one. Right? Now the database server will see a bunch of ones, and this allows the database server immediately know that I am querying one, for example. So this is not private. So what do we want? We want that no matter which numbers the client sent here, the database server always sees some random stuff. That's what we want. Okay, so yeah, so before I dive into this like results and details, I want to contrast our model with the classical ones just to show like the trade-off, like what benefits we get and what we trade off. So the shuffle model here, basically, we still need to assume non-collusion assumption between the database server and shuffle server. But the key benefit is that we do not replicate the database. And this is very important in industry deployment because let's say Google or like some banks, they have some database that they own and they do not want to share this database with another entity. So this is very important in practice. And also this shuffler or like shuffle server can be instantiated in the distributed. So it doesn't need to be like a physical central server as some entity. It can be like, for example, Tor network where you distribute a bunch of volunteer servers at where in the world. Okay. So in such model, we show that we can get security benefits as in the multi-server or two-server setting. And we also can get efficiency benefit as in a multi-server setting. So recall that the multi-server setting has better efficiency. But now like after we introduce this shuffler here, we can get those benefits as in the multi-server setting without replicating the database. The first result is a feasibility, like theoretical feasibility result. We show that single server PIR with information theoretic security and sublinear communication is like theoretically feasible. And the downside of the result is that it requires too many clients querying the database at the same time if you calculate the constant. So our second result is that if we can relax this information theoretic notion here to computational, we can get a peer in the shuffle model that has concretely small communication and computation, and this requires a reasonable number of simultaneous querying clients, let's say 1,000 or 10,000. That's very feasible in applications like Google search. Okay, so I'll expand a little bit on both of the results before jump into the details. So here concretely, we can get a single server peer protocol that for any constant gamma, there is a protocol with n to the gamma per query communication and computation, assuming there is polynomially many clients accessing the database. But here the security we get is like 1 over poly n instead of like exponential, a negligible. Yeah. Yes, so like I hide the gamma in this poly here. So because I want to make this like look more simple, but like you can think of there's like some gamma factor hide in this. Statistical security. Yeah, it depends on the number of clients. Okay, so the second result is that like how efficient our program is. So if you compare with the recent state of the art, single server, single database server PIR scheme, like we actually achieve like much better data points in this graph. And like this gray part is a non-privacy, so it's like closer. Okay, so both our constructions rely on a core idea called split mix. So I'll now first spend like 5 minutes on this. Before I go into this, any questions before? Yeah.
Like, how exactly do you define security in the shuffle model? Like, is the adversary trying to figure out just any one person's one person's index, or do they have to find all of them, or what?
Yeah, great question. So here we want the property that for any set of core indices here, the server cannot distinguish this. So the server always see random stuff. So even if, let's say, all these clients query 1, and in another setting, all the clients query 2, the server seeing the messages here cannot distinguish between the two cases. Yeah, so it's like much stronger, for example, than differential privacy, right? Like we do not need like the indices between the two cases any relation. They can be arbitrarily different, but we still guarantee the view of the server is the same. Yeah. Okay. Okay, so what is this split mix? It actually comes from a different problem called secure sum. So in such problem, we have a bunch of clients, and then a server wants to compute a sum of the inputs from the client without learning each individual numbers. Okay, so to do that, we'll take some field, let's say ZP, and then we additive secret sharing the value in Z. So for example, like let's say 5 in Z20 is additively split into 4 plus 10 plus 11 mod. Okay, now we will input these shares into the shuffler. And now the shuffler just randomly permits shares and then deliver them to the database server. Oh, sorry, here it's not. It's just like a server who wants to learn something. Okay, so server can sum up all this, and this is correct because it's correct. It's very easy to verify. And the key point is that these shuffled shares also reveal nothing about each individual input to the server if you have sufficiently many clients and if you split the shares into sufficient many. Okay, so the intuition behind this privacy is that since there are so many ways, so after you see the shares, there are so many ways to partition them, and the server has no idea like which partition results in the actual input configuration. Questions? Yeah, so let's say here like we have 51038, but like in another case maybe we have like 11438, something like that. But if we like split each share, like split each input into active shares and we shuffle them, like after the server sees the shares, like it can try to like let's say use these 3 shares as the first client input, these 3 shares as the second client input, but there are like so many ways to do them. And like intuitively, the server cannot figure this out. Okay, so the security against server is parameterized by 3 things. We group size, and we, yeah.
P to be any integer?
P to be an integer.
Any integer, or because you use the example P is equal to 20. I'm just wondering if it can be in fact an integer or just big 20 for this example.
Oh yeah, just an example. It can be like any integer.
As you said, it does not have to be.
Yeah, it does not have to be. So here, if you have the additive structure, then that's fine. So it requires the algebra structures is additive and like then you can swap of the addition. That's it. Yeah, basically it's just a group. A group is fine. Yeah. So, okay. So basically, that if we want to get security, we do not want the group size P to be too large, and we do not want the number of shares to be too small. For example, 1 share, like basically do not it's not private at all. And we want there are sufficient many clients to get past that. So keep this in mind. I'll get back to this later in the PI construction. Yeah.
I'm sure about the choices of KS.
Mhm.
I can understand that K cannot be too small, and I feel like K maybe has to be security parameter.
Yeah, yeah.
But then why? The number of clients also has to be sufficiently many. Like even if you have 2 clients, and each client split into like K shares, and now you have 2 K shares, and then you like kind of taking a subset sum.
Yeah, yeah. Like here we assume like let's say we fix sufficient number of clients, and then we can vary P. Okay. So it's not that. Yeah, I'm not saying that like you vary P, C like at the same time.
I see.
Yeah. So like in your case, if you only have 2 clients and then you split into like sufficiently many shares, that can still be secure. Yeah.
So with like with more clients, then maybe you can take a smaller P of more.
Yes, yes. Okay, so the key construction paradigm is that we'll view the multi-server PIR scheme under this additive sharing paradigm as before. So what does that mean? So let's cover like what multi-server PIR look like. Let's say we have 2 non-coding servers, they each hold database, And a client who holds the index I, it like actually split this index into Q1 and Q2 and send to the server. So the server just needs to plug in this Q into like their database answering their answering algorithm, which I denote as P of X here, and then send back to client. It doesn't need to know whether this is the first share or the second share. It just see a share and then plug into PX and then answer it. That's it. Okay. So now if we have, yeah.
So with the, it's like, how do you recover the answer?
How do we reconstruct the answer? Oh yeah, so you can just add A1 plus A2.
So it's the same database.
Same database. Yeah, you need to replicate the same database at the servers.
Then take I, you split into Q1 and Q2.
Mm-hmm.
Those are identity.
Yeah.
And then you send Q1 to the first one, Q2.
Yeah, so like these two data are the same, and then these are added secret sharing of the index. You can think like that. And then each database server will just plug in this Q it receives to some answer function that is related to the database.
This answer function guarantees that when you sum up A1 and
Yeah.
Q2, you get back.
Yeah. So here I abstract this as PX, but it can be complicated than that. Yeah. Okay. So now if we have many clients, I draw 5 here, and then they have arbitrary query indices, we can let them like split their queries as in the 2 server setting. So each client split I into Q1, Q2. Then these queries are sent to the shuffler, and the shuffler deliver them to the server. And what do we get from the split mix? We get security, right? Like it's like exactly the same picture as before. So that's the like construction paradigm, but there are like actual challenge we have when we, like instantiate this paradigm with the PR protocols. So that drives the first result. Okay, so to actually build like a concrete protocol, we need to find a multi-server peer that fits for the parameters P, K, and C, right? Let's say we fix C, and then we really need to find like a K server PIR where the subqueries of the PIR is in ZP. And this is the first step. And the second step is that we really need to prove that, like, okay, like we get statistical security from whatever the PR we use. Okay, so let's focus on, yeah.
For the earlier example that you showed, just about the additive, like when the query is a sum of everything, can you achieve better than longer poly-n statistical, or can you achieve exponentially small difference in attributes, or even in that case you cannot do that?
Okay, so the construction I cover here, like we have a general construction, cover here cannot achieve that, unfortunately. Yeah, but in the paper we do have some slightly different, I mean, like a construction in a different way that has sublinear communication and exponential security. Yeah. But the communication there is really not very good. So yeah.
So in some sense here, you get security that's similar to the split server case because the server sort of like sees independent random points.
Yeah, so the server, so you can think of these subqueries Q1, Q2 as the splitted numbers here. Yeah. So the server will, yeah.
But in the other music, you have two separate like what helps you get split wrong.
Oh, right. So like here, like in like privacy hold only are not coded, right? Yeah. Yeah, I merged them into one, but the difference is that they are shuffled. So the shuffling really gives you the power of privacy here. So if you just deliver these shares in like unshuffled form, it's like completely insecure because of that. Yeah. But when you like shuffle all these shares, you suddenly get privacy. That's the essence. Yeah. Any other questions? Okay, I'll continue. Okay, so we identify two server peer protocols that has such property with both log and query size and square root and answer size. So we want the query size to be really, really small because we we don't want P to be large. So that's the reason. Okay, yeah.
For the answer side, there is it possible to, I don't know, but is it possible to get logged in on answer side? Or?
So the best answer set can be like 1 bit, but yeah, but like we understand this protocol because there's some later reason I'll talk about. Yeah, but like if you consider multi-bit, the best answer set is actually 1 bit. Yeah. 1 bit from per, like 1 bit per server. Okay, so if we plug in this to like this active secret sharing paradigm, then are we done? Unfortunately, there's like a problem that like 2 share is not enough. And even if you have exponentially many clients, 2 share is still not enough. So this is a simple example to explain the intuition. So let's say all the clients, they input 0. And in another case, all the clients input 1. And in the first case, 0 can only be split into 0 plus 0. And sorry, 0 can be split into 0 plus 0 and 1 plus 1. But 1 can only be split into 0 plus 1. So even if you have exponentially many clients, the server seeing all these shuffled 0s and 1s can still distinguish between the 2 cases by counting the number of 0 1s, right? So 2 shares are unfortunately not enough, and this similar attack can also generalize to ZP where P is larger. Okay, so what do? We can try to like modify this PR protocol to generalize to K server, but this will unfortunately get a much larger answer size. So for K server PR that has added property, it requires answer size n to the K minus 1 over K. So even if K is, let's say 10, it's almost similar to downloading the database as a whole. So our technique that I'll cover next is to randomize the query index for this two server peer using an outer layer of peer. So I'll explain this in the next 2 minutes. Yeah.
So for the first time we had the issue with 2 shares, can that get ability to take P to be larger than the size of the database?
You can. You mean? Oh, I mean like here, even if you take like a large P, like this problem still exists.
P spread from the size of the database?
Yeah. So like we like basically like this attack can be generalized to any ZP. With 2 shares, with 3 shares that's different.
Oh,
yeah. Here we're just saying like with 2 shares, this attack exists for any client and any P. Yeah. Okay, so the result of this technique is that we can bring down the communication still back to root n with polylog overhead. Okay, so now I'll cover this technique. Okay, so recall the problem we faced in the 2 share setting is that if in the 2 cases the indices are far apart, then after you split into 2 shares, it's still like far apart because like, for example, this counting 0s and 1s. Okay, but if we take a step optimistically forward, let's say if we have some query indices that are closer, let's say for a string like this with length n, like the added distance between the strings in the 2 cases are root n, for example. Then after splitting everyone into two shares, we can actually get statistical security. And this is something that we proved. Okay, but the problem is that how do we like make them to be close, right? You cannot say that, oh, like this client, you don't query one, like you query two, but this client do want to get the answer to one, right? So we'll do this via a randomization technique using another peer. Okay, so now take like your favorite multi-server peer algorithm, and you input any index into the query algorithm, and then you get, let's say, 3 subqueries, Q1, Q2, Q3. If you look at each of these queries, it's uniformly random over the space that consists of all possible subqueries. So let's say our PR query is of 4 bits, and then the space will be like 2 to the 4, like 2 to the 4, where you have like string ranging from 0000 to 1111. And now after you run the algorithm, maybe Q1 will be like 0100, but it will be random over this space. Right. Okay, so now we will utilize this property and randomize the indices using any altered PR scheme. So like this property holds for any peer. Okay, so each client, they will locally run a multi-server PR algorithm on their index, and then they now have a bunch of subqueries, Q1, Q2, Q3. Next, we're going to interpret these subqueries as the indices in the range n star, that is the size of the subquery space Q. Okay, now if you look at indices I star and indices I, so what happens? So I can be like arbitrarily different in the 2 cases where we want to distinguish. But I star, like each of them is random. Okay, so yeah. But now we want to like answer to each of these indices, right? So we'll build a database that consists of all possible answers in the outer PR algorithm. So let's say this subqueries is 0001 is interpreted as index 2 in the database of size n star. Then we're gonna basically like sort all the possible answers with regard to the subqueries. And that's the database we're gonna use to answer I star, I1 star, I2 star, I3 star. So concretely, we're gonna run this using the 2-server protocol that we said before. So now like we still have 2 shares, but the 2 shares are derived from each of these random indices. Okay, so just to summarize, it works as follows. So each client, they locally run any multi-server peer, and they get random queries, each of them are random. And we interpret this as random indices in a database of another size. And we show that these random indices actually has like closer added distance between the 2 cases if we have many clients and like suitable P parameter. Okay, and now we run the 2-server PIR using in the shuffle model to this pre-built database. And then each client can get an answer to this I1 star, I2 star, I3 star. And then it's interpreted back as a subquery, and then reconstruct the result to I1. Any questions? Yeah.
You still super share I1 star, I2 star?
Yeah, like here, like I secret share I1 star, I2 star as in the 2-server peer I described before. So here, like this blue box, so let's ignore the part. Just this blue box is just running the previous 2-server peer with the shuffler. That's it.
the star queries random enough usually to share them?
Like if you have like I1, I2, I3, pretty random.
No, no, no.
Oh.
We are inside the blue box,
Uh-huh.
right? And you're saying that inside that blue box, each of those subqueries that you generated by running the outer PIR scheme, you still need to super share them to run your.
Okay, great question. Great question. Yeah, yeah. So here, like if you, let's say we do not secret share, we just send them in random order to the server. It does leak some information. And yeah, and we show that like by secret sharing into only 2 shares, you can get status security. But if you send them like without secret share, that does leak information. Yeah, and the reason behind that is actually, even if each of them is uniformly random, they are correlated. So I1 star, I2 star, I3 star, they're actually correlated. So you need to use the secret sharing to basically break this correlation, so that it creates some like uniformly random stuff that looks uniform.
Now you say that you could use two shares, and I think previously you mentioned that the 2 shares is the problem.
Yeah, so if 2 shares, okay, yeah. If I use 2 shares on these arbitrary arbitrary fixed indices, let's say I have 2 cases. First case, every client's query 1. Second case, every client's query 2. And I throw in this 2 server tier, split everything in 2 shares, and send it to a shuffler. This is not secure because counter example we saw before. Yeah, but here is what we do. We first randomize these 2 sets of queries, and then we run the 2 server pair on a set of different indices. Yeah, the trick here is that you can still answer back whatever the client wants to query for. Yeah, so that's the trick. Oh, like it depends on the PR output. Because here this is the space of the subquery, so it's poly n. Yeah, but depends on the constants. Like it can be different. It can be like n squared, n cubed, something like that.
What if the server just makes up a much larger number of fake queries? Like I will query them. This shuffle server will query the database, but it will not use those answers.
Yeah, that's another.
I use the noise to hide.
Yes, exactly. So that's something you want to do if you have a few number of clients. Then you can always have the shuffler add a bunch of noise so that you can still answer it back. Yeah, the shuffler can like add like whatever it wants. Yeah. Okay, so just to summarize, using this paradigm with any outer peer and like this server peer that I showed before, we get one-word polystatic security and root and communication. But if we use something fancier, which I'll not describe here, we can get the communication down to n to the gamma for any constant gamma. So this corollary is actually a generic construction. So for every gamma, like you have such a protocol. Yeah.
Why did you choose this specific chosen? Because I guess it's additive.
Yeah, we want, okay, so let me go back to this.
And then like additive with greater.
Yeah, so like we want to have like several features here. So we want the subqueries to be additive in order to fit in this paradigm. And we also want the query length to be small. So why is that? Because we do not want the P here to be too large. Yeah, so this is the 2 requirement we want to have for selecting such a peer.
Are there other like multi-server peer that also satisfy these 2 properties, but like other trick?
I think the beam like BIK family of protocols, they have like log n, but I don't think others they can get down to log of n. Yeah, there are like very simple multi-server peer, but the query size is root n. Yeah. The problem with root n is that like when you interpret as ZP, it's like pretty large field. Okay. So this is a theoretical part, and our next result is a concretely efficient one. And the insight is pretty simple. So we focus on statistical security before, but now we're going to relax it to computational security, and the hope is that we'll get better efficiency. So let's see. Let's say so we have 100,000, 10,000 clients, and if we restrict us to statistical security, then we need like thousands of the shares to actually get 40 bits of statistical security. And if we can like relax this to computational security, then we can largely reduce number of shares, and hence this will improve the concrete communication per client. So for example, let's say we have 10,000 clients, query database at the same time, then we can reduce this 2.7 thousands to only 37. And 37 is actually pretty practical in applications. Okay, so this is our like high-level view of our results. So in this part, we just study the computational security for split mix. And from that, we can build black box, we can build this build secure aggregation protocol in the shuffle model and single server peer protocol from this assumption. But in this talk, I will only focus on the PIR part. Okay, so now consider extremely simple multi-server PIR. So let's say we organize the database as root n by root n matrix. So each square is just 1 bit. And then the client, let's say I want to query I will interpret this query as like one hot vector. So let's say I want to retrieve the yellow item, then I'll retrieve the entire column and interpret my this column as 0010. Okay. Next, the client will just split this one hot vector additively over Z2, and then send the shares to each server. And each server can answer back by just doing inner product with the database, right? Okay, so that's it. And our claim is that if you shuffle the subqueries Q1 up to Qk here and send to the server, we get computational security. Okay, so let's see why. So the assumption we're going to base is called syndrome decoding. So syndrome decoding problem can be succinctly described as follows. So given a matrix H and a target vector Y, we're asked to find few columns in H that adds up to 1. So like, how does this relate to what we saw before? So let's assume for a second, we only have one client. And this client shares or subqueries are mixed with a bunch of uniformly random stuff. So now we will view this target vector Y as the one hot vector the client has. And we'll view these yellow vectors as the secret shares of the of Y. And then we throw in a bunch of random noise, that's the blue part. And like according to syndrome decoding, this is computationally hard. I mean, like it's computationally hard to find like a few vectors that adds up. Okay, so we generalize this assumption to something called multi-disjoint syndrome decoding. It means that, let's say we have one of target vectors, one up to YC if you have C clients. And we claim that it's computationally hard to find to find a few vectors that each set adds up to Y1, Y2, etc. Yeah.
You have n counted, how large?
Yeah, so if we have n, then you need to make, so there's a security parameters that relate to how many noise you need to add. And so you need, okay, so there are two parameters. So every Y1 needs to be shared into sufficiently large K shares. Plus there's a parameter lambda that means how many nodes you add to the shares. So if you keep these two parameters in a good regime, then you're going to get computational security. Yeah. Okay. So as a result, this computational peer in shuffle model looks like this. But just a note, like there's no like inner outer parameter. We're just shuffling this simple additive peer record. So every client split the one hop vector into a bunch of shares, shuffle them, and then deliver to the database. The database can answer each course without knowing like which shares, right? And then it sends back the answers, and the client can shuffle permutes them back, and then the client can reconstruct the answer by just additively add those. Okay. By the way, here like the server needs to take the role of inserting random noise like that before, because I need to make up this blue part. Okay. So yeah, so this is our performance. If we have 1,000 clients, like we can reduce this computation per client to something like less than a second for like 8 GB database. And if you have more clients, this cost is going to reduce more for the communication. And the intuition is that you can split into less number of shares if you have more clients. Okay, so that's basically the, yeah.
Running thing for IM 1
BIK04.
Yeah, for the multi-server.
Yeah, two-server and multi-server.
Yes, it's for the version when you use the LTM, is running that or the.
This one you mean?
Yeah, once you shuffle them and you send them to the server, so that's the base of that same.
Oh, sorry. This only needs to be based on this simple multi-server peer. So this is not the BIK. It's just like the classic multi-server. Yeah. So here, for example, the query size is actually root n, because you have like one hop vector, and the answer size also root n because you retrieve entire column. Yeah. And so the second result is not related to the BIK construction. It's just shuffling the small. Okay. So I guess that's the end of my talk. One thing that I want to briefly mention here is the shuffle model actually, like to help us achieve something that is probably impossible in the standard model. So in the standard PIR, you basically need to pad every item into the same size. So let's say you have a database where the first item is 1 kilobytes, but the second item is 10 kilobytes. Then you have no choice but pad like everything to 10 kilobytes, which is the maximum recurrence in database. But in shuffle model, we show that you actually don't need to do that while getting security. So you not only get security against the server, but also you can also hide from the shuffler, like the length of the record you want to retrieve. Yeah, but I don't have time to cover this. We can discuss offline if you're interested. Okay, so to summarize, like basically here in shuffle model gets the benefits, the security and efficient benefits as in the two-server model, while we eliminate one database. So we eliminate the replication of database. And also the shuffle server can be distributively run. So in practice, this is easier to enforce the non-quotient. And also there's no storage overhead at any of this. Okay, so that's the end of the talk. Thanks.
Part where you showed computational pulse. What's preventing you from splitting into like a 3D cube of to the 1/3 in each dimension? And I will have two vectors, one.
Oh, you were,
categorical-
so you represent the database as a two?
Yeah, for example.
Okay, yeah, that's a great point. But I think the problem is that how do you answer the query becomes a little bit unclear. Because here, like, you can answer the queries like without knowing, like, like which yeah, let me think. Yeah, so for example, let's say I get a share with n to the 1/3 that, like, should I apply this share to like the first dimension or second dimension, third dimension? It's like sort of unclear because you have two level of uncertainty here, but here you only have one level. Like basically the share, you know that I'm only going to apply this to select the columns. But in that case, you have another uncertainty, like whether I'm going to select this, or like this. Yeah. We can discuss this offline. Yeah.
The shuffle server, you were mentioning at the end that it's actually it can be realized in the distributed.
Yeah.
You see a difference?
Oh yeah. So like for example, let's say MixNet. Like MixNet, you have like a bunch of server layer by layer, and each set of server they shuffle messages. So you can think of, let's say I have like everybody send messages to the first layer of server, and then the server shuffles the received messages. I mean, like they do not shuffle all of them. Maybe some of them shuffle a subset of them, and then they send the message in the second layers of servers, and each server shuffles the messages they receive, and on and on. So it makes like the guarantee is that if you have sufficiently number of layers, then you can get a permutation that is fully random.
Shuffle servers together, learn some information about the queries.
Oh, okay, good question. You can encrypt the queries using like TLS, for example. So yeah. So you can assume that there is a symmetric key between the server and all the clients. Yeah, and or you can assume like the server has a secret key and everybody has a server key.
I see, yeah, because if you instantiate TLS, then there's
Yeah. So you can sort of think every query is encrypted using server's public key, and then server can decrypt.
I guess not have any online offline phase.
Online, sorry,
Offline phase pointer. Because in some PI protocol they have offline phase where there's something before we go to online phase.
Yeah.
People first, so it's for you don't know. The thing is just
yeah, like I'm hiding here behind the abstraction for simplicity, but we do have preprocessing for both. So for the first result, this is just inherent from the BIK protocol. So the BIK protocol also has preprocessing, but here we just like abstract this. And the like they do preprocessing to get like sublinear computation time. And in a second, I can talk about this a little bit because it's simple. If you see like this, let's say I split the queries into like k shares, and any k minus 1 is independently random. So that means the server can preprocess, basically the client can send like a seed to the server saying that this is my first k minus 1 queries. And the server can just preprocess them. And then whenever the client wants to actually query a thing, it just derive the last string from the query index. Yeah, so this way you can also do preprocessing and shift k minus 1 over k workload to the offline. Yeah.
Another question about like the distributed shufflers setting. So also, I assume there you would want some mechanism to make sure that those participants aren't like messing with the queries, like, like basically like you need like authenticated encryption or something, because you want to make sure that they're not, like, you ask to see the first entry and instead they change it to
Yeah,
you're gonna get the first entry.
Yeah, I think like generically, I think PIR in general doesn't consider much about malicious server. There are some works, they do have some work that has like malicious server, but it's very inefficient, unfortunately, because it's actually very hard to prevent. So let's forget about sharding. So let's say just one server, one client, and the server can apply adaptively chosen attack for the client by doing, let's say I corrupt the first item, and then I'll observe whether the client queries again, something like that. So it's actually very hard to prevent in practice. And the same issue also applies here in the shuffle model. So if the shuffler do something bad, it's like the server doing something bad. So it's hard to.
I guess maybe I'm just, maybe you can like are willing to trust the server because it's like Retrieval or something. But if these like shuffler participants are just like random people like from Twitter, like maybe you care more about ensuring they're not.
Yeah, but that's a good point. Yeah, that's a good point. You can also like use Shamir secret sharing, but the problem here is that it's very hard to like prove like basic security on standard assumptions. Actually, like using Shamir secret sharing, shuffling them is first considered in this split paper. They also mentioned this for peer protocols, but the protocol is rely on like non-standard computational assumptions. But like using Shamir sharing sort of solves this problem a little bit, right? Like you get like fault tolerance against the faulty shuffler. Yeah. Or maybe you can sign the mess. Oh no, you cannot. Yeah. Okay. Yeah, that's a valid argument. Oh, there's another question. Yeah.
So in the beginning, you mentioned that when you don't have a primitive computation, you lose some security. Now,
I lose some. Can you tell me which slide?
no, that was way in the beginning when you introduced the shuffle model, and I was wondering what you lose if the shuffler does not perfectly shuffle. For instance, he always shuffle only the last.
Oh yeah. So like let's say the shuffler does not perform like a uniformly random permutation among all the clients, right? For example, it shuffles some client's message, but not the others. And we prove that this still guarantees some sort of privacy against the database. Yeah, even if the shuffle server does not use like a perfect permutation.